I have been reading articles that that future is going to change so fast, so soon that people will be hired by AI. Did you hear that? Anybody? You can type also. Did you hear that? AI is going to hire you. So, but the problem is, imagine AI hiring you means you are just following the rote job. In order to avoid rote jobs in future, that is going to be an issue. You have to know the why of whatever you are learning. And here is a very, very important topic called matrices or linear algebra, which is very fundamental for understanding how and why of big data analytics, which is the foundation for AI. Okay, so my purpose is really to impress on you that learn the foundations, learn the why aspects of data science. And here is one such concept, that is linear algebra, and the alternative name for that is matrices. Okay, all right. So given that introduction, there are three things that I really want to bring it up to you today. But however, due to time constraint, I will not be able to talk to you a lot of things. Okay, so maybe I talked to you in the message I posted today, early morning US time, which is in the afternoon tea time in India. Most of you come from US and India, and three things I said. So what's special about matrices, right? Why does it matter to you? Matrices are fundamental in actually the computer graphics, how the computer graphics are done. Fundamental for computer graphics. The 3D animation, the games, the editing of pictures by the Adobe group of software. All these things are made possible by matrices. You won't believe it, but that's the truth. I'm going to show it to you. Okay. The second part is, you all know that big data is fundamental for the new world of data science. Big data analysis is fundamental for the new world of machine learning and AI. And fundamental to that is matrices again. How do we handle big data in a credible way, mathematically, correctly, and all those things is actually done by matrices, including the reduction of dimensions. Okay, because big data is huge dimensions, but it has to be intuitively appealing to all of us, including the analysts and your managers. So that's where the matrices come into play. For example, the principal component analysis. All right. So the third part is matrices are fundamental, and Tensor Algebra, which is the new world AI application from Google, Tensor Algebra, Tensor Analytics, TensorFlow. And in fact, it is so important, so relevant that Google has invented their TPU, that is Tensor Processing Unit. And there also the matrices and extension of matrices to a different set of operations. Extension of matrices to a different set of operation is what is called the tensor algebra. So we want to learn these things because because of the importance of all these things, right? The three-dimensional or multi-dimensional manipulation of data points. Multi-dimensional manipulation of data points is algebra. Matrix is done by matrix algebra. The multi-dimensional analytics, the big data analytics, is fundamentally matrix algebra. And the new world TensorFlow operations and TPU calculations like CPU, GPU, right? That's what the Google has invented, and Google has brought out that processing unit chip. That is also fundamentally an extension of matrices. So for all these things, I hope you are as excited as I am in learning, articulating, and using it. Are you with me? How does that sound? I like people interaction with me. You can even ask any question. I don't care. I love it when people interact with me as a teacher and student. Ah, the student is the teacher sometimes. Okay, so the student and the teacher. How does this sound? This is my purpose today. How does this sound? So I introduce you to matrices foundations. Basically, I'll go through some foundation because we have very limited time. It's already we have 7 minutes into the introduction, 7 8 minutes into the purpose, and we are going to spend probably another 50 minutes. But the point is really as dedicated people of data science and the new world, new technology, machine learning and AI, artificial intelligence. I'm pretty sure you feel just getting this, the fundamental questions in your heart will drive you to the right place. Okay, so that's my purpose today. Okay, so get you interested, get you excited about the science, data science, and the new world of machine learning and artificial intelligence. How does that sound? Give me some input. Type, please type. Nobody is typing it. Nobody is talking. I want at least people to say something. It doesn't matter what it is, just say something. It may be very simple issue. So go ahead. I'm even opening up the whole audio for you, all of you. So please talk to me, interact with me. Otherwise, it's not interesting, isn't it? So you have to say by name here. Please go ahead. Asking you to interact. At least type, man. Just type at least. Okay. Nobody is responding to me. I think it's
Kaviraj speaking.
Kaviraj. Yes, Kaviraj. Go ahead.
So I'm actually a newbie into this field. So being from analytics background, I'm a BA developer. So sort of using my visualization knowledge to bring into data analytics. So my quick question is matrices and linear algebra is sufficient for getting into the data science, or do I need to brush up with the probability and trigonometry, although
that's a very good question. That's a very good question. Data science is a huge ocean, right? I mean, you have to know mathematics, you have to know statistics, you have to know computational, languages, and you have to know the human behavior too, because you have to interpret things that are relevant to the process. And the process is generally changing human behaviors, right? Doing the right thing for the people, doing the right thing for the environment, and including animal husbandry, right? Absolutely, your question is great. So the point is, it is not. That's not the only thing, but that is one of the things. So it's like a car, right? The car needs many things. If you want to say, hey, can I drive the car? If I have the engine, can I drive the car? But that's not enough, right? You need the tires, and then you need the oil, things like that, right? And you need a farm so that you can sit inside and then drive the car from one place to another place. So yeah, I don't know. Matrices is the engine, but you can say something like that. Matrices is the engine. Let's say matrices are mathematics is the engine, statistics is the engine, but then you need other things like the oil is probably the computational methods, the programming languages, and you got to have the tire, you got to have the body of the car, and you need to make sure that the processing, the engine is working with the oil and the tires and the farm and the driver. All right. So did I answer your question?
Yeah, perfect. And in that case, let me put the question in this way. So, do we have any prescribed list of things which are all the foundations to get into a data science field?
Yeah, the thing is, it takes time and patience and experience, continuously working on problems, right? So let's take it as step by step. But even with the step by step, you are right. There are some few things that you have to absolutely concentrate, and you have to work with the places and where they will teach you all these things. And like I'm talking about mathematics. Right mathematics. So there is a lot of mathematics is again another version. Don't go into mathematics. Try to learn everything. No, specific topics concentrated that are relevant for data science is what you need to focus. Okay, so in that sense, for example, matrices is one of them. As you said, probability and statistics foundations are another one of them, right? The third one is computational languages, Python and R, SAS. These are SAS is now becoming less and less, less and less. I don't want to say important, but that's where it's getting there, to my thinking, right? So Python is becoming fundamental to data science. R is becoming fundamental to data science. So And then on top of it, the institute wherever you are going to learn these kinds of sciences should encourage you to talk about questions, ask right questions, challenge right way of thinking, with the faculty, with the students around and so on. So it has to transform you into a thinker of data science so that you can actually independently think, independently talk, and articulate your good points or ask good questions, right? So all these things have to come together in your training. It's not just enough if you know one part of it. And did I answer your question?
Yeah, absolutely.
So there are 4 things I mentioned, right? Fundamental. One is the mathematics and statistics of it. Second one is the computational aspects of it, languages, especially the Python and data or language. Third one is the hardcore machine learning, statistical learning, AI concepts. The fourth one is as the ability to transform yourself with the ability to ask good questions for which you need the right community. So the institute, the school that teaches you data science, they should encourage you to work in that manner. So those are the 4 things. Okay.
So is it good to pursue a degree and getting into the data science, or we can learn on our?
Do you have an undergraduate degree?
Undergraduate is there? Yep.
Yes, if you have undergraduate degree, you should be fine. But my point is, you have to talk to, you have to work with the right people, right institute, the institute that has the right vision for the field. Okay, so obviously I'm not trying to sell here, but nonetheless I do want to say that I come from Institute of Analytics, and this is sponsored by Institute of Analytics. We pride ourselves, that we provide that kind of environment to the students. Okay. Anybody else?
Okay.
Thank you. Any other questions? I love this guy, Mr. Kaviraj. I appreciate it. Thank you very much. Because this is what makes it interesting. Otherwise, I come here, I lecture, and then you go home. That's not interesting. That's not really exciting, in terms of learning and again engaging. See, be engaged in your work. Be engaged in your learning. Be engaged in your process. Don't just be another point, another data point, another individual. So from that point of view, I appreciate what you did. Thank you very much. Any other question I can answer? Actually, this is great. Don't worry about learning the matrices. I'm going to teach you that, but just talk to me and start typing also. I like people typing in the chat area. Do you see chat area on the control box? Do you see chat area? I'm not able to hear. Somebody is trying to talk.
No, there is no chat window.
You don't have a chat window? I'm sorry about that. Why is that? There is a control box you have, right? There is a control box you have.
There is a control panel, but there is no chat area. That's the problem.
I see. I'm wondering why. Let me see options. Maybe in the options, attendees can chat. Okay, let's see whether you see now.
Yes, now.
Cool.
Now it is visible.
For your arts content, start interacting with me in the chat also. If you are shy about talking, you shouldn't be shy. This is your world, man. This is your world. Okay, so don't hesitate. Don't be shy. Let's talk, interact, learn, go home, enjoy the day. Okay. All right. I look forward to hearing your voice and seeing your chats. All right, now what I want to go is, okay, let's start the process of, I want to challenge you to think in the following way. You might have, in Adobe or any software, you can, simple thing, like, the fonts. You can move the fonts, you can scale the fonts, you can rotate the fonts, you can skew the fonts. Skew is also called shearing in some applications. This is the foundation of graphics, computer graphics, okay? And one thing, computer is not really drawing these things. It implements matrix transformations of original points. Does it make sense to you? This computer is not really drawing these things. It's really implementing matrix transformations of original points. So alternatively, I can say computer drawing is actually matrix transformation of points, period. End of the statement. So how is this computer is doing it? It's basically implementing matrix transformation of original points, okay? and it speeds up, it's fast, it can do any kind of wonders, it can rotate this point, anything, all these things are matrix transformations. So there is just a mathematics. This digital world is, everybody says 0, 1. The digital world in static is 0, 1. But in movement, in shape, it is really the mathematics. The digital world is the mathematics. Okay, so how is it done? So what is this matrix then, right? So is the foundational question clear to you? In any 3D graphics, this is only 2D, right? Even in 3D graphics, that's the same thing. It is just a matrix, data points being transformed from one state to another state. That's all to it. So the new world of digital world is all about really not only 0, 1, that's one part of it, there's a computational part of it, that's a representation part of it, that is the visual part of it, but how the visual happens behind the screen is through mathematics. And that mathematics is really the matrix transformations. There is one part of it, that's the graphics part of it. And you probably have seen like this. Everybody in the world knows about the solving systems of equations, right? Everybody knows it. Anybody who doesn't know this one, what I'm talking, you all heard of it, did some work on it, systems of equation. Am I right? Can you please in the chat say yes or no or something like that? I appreciate it. So again, it is the systems of equation, let's say x plus y plus z equal to 6, 2y plus 5z equal to 4, minus 4, 2x, there is no x here, right? 2x plus 5y minus z is equal to 27, okay? And that system of equation can be written in this form, and this is called the matrices. On the left more, 1, 1, 1, 1, 1, 1, 1, 1, 1, 0, 2, 5, 2, 5 minus 1. This is called the matrix representation of this equation. These are the variables to solve, and this is the right-hand side value. Again, the matrices come into play. Okay, so two things I have mentioned so far, right? The third one is, dimension reduction, right? We talked about, I said, fundamental to dimension reduction is matrix theory. So, for example, I'm going to go to, let's say, PCA, just in multivariate analysis. I'm giving a big word, multivariate analysis, but the point is, the real life, the data comes in huge number of variables and huge number of records. So how do we reduce that meaningfully? That's what, that is the PCA is that one, and that is achieved by matrices. So for these reasons, we want to learn a little bit of mathematics about matrices. That's what I want to continue to introduce you, okay? There's a lot of things that I can teach you, but I just want to introduce this concept to you so that you get excited, and then you have a chance, you get convinced yourself that oh, this is good, and maybe I should learn this thing, because the future is all about, believe me, IT people. A lot of IT people are here, I'm pretty sure. How many of you are IT, pure IT? Can you please say yes, 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 or no, 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 something like that in the chat area? Nobody is doing anything in the chat area.
Yes.
Are you not able to type? Please give me. Can you type?
I'm using mobile, so I can't use computer. So I have connected it through.
If you don't have access to your computer, you are listening, that's fine. But those who are using laptop or whatever computer, you should be able to type, right? Can you please type?
No, we are not able to type.
I'm sorry.
We can able to see the attendance list, but not able to type anything.
Oh, you chat in the chat area, you're not able to type, huh? Okay, let's forget about chat today. We'll only talk. That's fine. And maybe there is a setup that I didn't do it correctly. Maybe next time I'll do it. I'll figure out before I come on the call. Okay. Now, so I mentioned, like, for example, so the final example I said, data reduction, data handling, data analysis requires matrix algebra. And the fourth one is really the deep learning. I'm not going there, which is what the TensorFlow is. But, we need to understand enough of matrix theory to go into the tensor algebra. We don't want to go there now, okay? Somebody's trying to say something? Okay. All right, and feel free, please, to stop me, get your attention, speak to me. That helps you. So let's go back to understanding what is it. So the point is, I said, the whole computer graphics is, all about matrix transformation. So let me do a little bit of that one for you right now. Before I go, yes, 1 second. Stay put 1 second. I want to continue to go back to that foundation I started talking with you. Okay, so we talked about the whole computer graphics is really matrix transformation that I'm going to show it to you. Okay, now. So I'm going to go into this particular link. Let's see. There are some really good notes that are available. I don't have to create or write. So let us say this is what you are working with some kind of a mechanical dog, right? And the mechanical dog is represented in three-dimensional form in these line curve, okay, line graphs. And you can see that every point, end point, is a three-dimensional point, right? And three-dimensional point in a simple way is represented like this, and in a picture way, it is represented like this. Okay, this is a cube, three-dimensional cube. This is in a picture of a mechanical dog. So if you want the transform the mechanical dog, like let us say, kind of as if it is going, walking up the wall on the left side or right side, or it is being elongated into huge size or reduced in size, for example, like this. All these things I'm just saying, it's all actually matrix transformations. Now, if you look at this, there are control boxes here in your application, in this case Adobe Illustrator, that does that work for you, but it's really in the behind the screen, it's doing a matrix transformation. So I know there are a little bit of mathematics that I'm going to talk about it, but don't worry about it. If you don't understand, no worries, because that's where you have to spend more time. But today my purpose is not really to grind you with why this particular angle is represented by cosine alpha times a and sine alpha times a. Okay, that's not my purpose, but you believe in me that it can be done mathematically, then it becomes a rotation, from here, this angle, rotation from here to here, this alpha to up to this point, increase the alpha by this, by a certain angle, certain ratio, then it is basically this transformation. Cosine alpha times a minus sine alpha times b is the x coordinate translation, y coordinate translation is like this. And that is a representation like this. Again, it's a matrix. Matrices are collection of rectangular collection of numbers. It's basically a rectangular collection of numbers, but I want to say more than that later. Now, that is about rotation, but let's go back to the simple one, proportional scaling. Okay, that's about rotation. Now scaling, I have this point a comma 0 here, b comma 0 is this height, so a and b is represented by this point. I want to scale this 2 times. Okay, I want to scale this 2 times. That is means this point has to go 2 times, means here, right? That is simply a matrix multiplication of the original point AB. The original point AB is here. Okay, so even though it's a triangle is given here, really think about it. This point is moved to this point. That's all we are talking about. Okay, so what we are saying is the movement of this point is done by this matrix transformation. So just multiply this, boom, it moves there exactly 2 times on both axes, x-axis 2 times, y-axis 2 times. Look at it very carefully. Now I'm going to say something very interesting, and if you understand this part, you are getting the hang of the matrices. Suppose I want to go 2 times in this direction, but 3 times in this direction. What will happen to these matrices? Can anybody give me an answer here? This is x-axis translation, extension, projection, scaling. This is y-axis. If I use only this part, this is a y-axis scaling. This is x-axis scaling. This is y-axis scaling. Nothing else is happening on these things. Okay. If initially I said, I move the point 2 times, on the x-axis and 2 times on the y-axis, which is b. That is moving AB to 2A to B simply means this. Suppose I want to extend 3 times x-axis but 4 times y-axis. What change will happen here in this matrix? Anybody? I want to see or hear.
It will be 3004.
3004. Excellent. Everybody on board? Emra, is that who said that? Excellent.
Shailesh here from Bangalore.
Oh, Shiva. Shiva? Is that Shiva who answered that? Sanjeev?
No, it's Shailesh. Shailesh.
Oh, Shailesh, welcome, Shailesh. Thank you very much. Wonderful. So that is the point, right? Suppose, okay, I want to scale 3 times x-axis, but half time y-axis. How will this matrix change? Go ahead. It doesn't matter if the same person can say the answer. Some people are quiet, they are just listening.
It should be 3001.
No, I said I said half. Oh, I see. Okay, because already 2 times is there. You want to say half means 1. Excellent. That's fine. I was looking in. So if the original point is there, I'm not extending it to 2 times. But if the original point is there, what would be here? What number should be here?
6001.
No. I'm saying original point is AB. I don't want to change anything. So what will be here happening? The original point is AB. I don't want to change anything. I don't want to change anything to AB. That means the output should be A and B here also, right side. What would be the numbers here?
1001.
Excellent. 1001. Somebody else said, talked about earlier. I don't know whether it is Miss Kala or somebody, Prema. Okay, because it's a female voice. So it is 1001. Do you agree?
Yes.
Okay. So this is the point. So any scaling is basically on the diagonal changes. Diagonal changes means scaling, simple. But based on which number changes, that specific, this is the x-axis, this is the y-axis. Based on the number that changes, that affects that axis alone. Simple. Got it? Everybody got it. Okay. So here is actually the non-proportional scaling. This was a proportional scaling. This is a non-proportional scaling. That means here original point is, on the x-axis 2 times you are scaling up, and then you are reducing the scaling by 50% on the y-axis. Yeah? Somebody's talking? Go ahead, please. Okay. Somebody thought I heard somebody talking. Okay. So that's why it is 2.5. So diagonals are about scaling information. Now, if it is a shearing or what is called skewing, that are the off diagonal elements. Get it? So shearing or skewing, same skew. Skewing is, is done by off diagonal elements. These are off diagonal elements. Okay. And, we will finish the graphics part of it pretty soon. And then I will go to solutions, systems of solutions of equations. And that sets up the big standards for you to move into the matrix very nicely, very easily. Okay. Now this is shearing, because what happens is, it is going to change the it keeps one of it keeps the scaling of the axis, but it is increasing the diagonals. That's what this means. The effect of this one means. Okay. So what happens is the increasing diagonal in such a way that it is bringing the diagonal to be the sum of these two to be the diagonals to be one of the axes is A plus B. Okay. A is this, B is this, B is this particular axis, and then by adding this, B additional units to the next, the original A point to B additional units. By putting 1 here, we are adding B additional units to A. Okay. So that is what is making it the slanted, skewed, or sheared point. So the original point AB is skewed or sheared to this point. So the graphics will look like kind of extended in one direction, one angle in a slanted way. Okay. So That's again an effect of how it is done in the matrix. Now, this is the second aspect of it. One is scaling, proportional or non-proportional scaling. The other one is shearing. The third one is flipping. What happens on the on one side, you want to take a mirror image, also called mirror image. Flipping is same as mirror image. If you want a mirror image, you do a negative number on the axis that you want the mirror to be. Okay, so if it is the x-axis is to be mirrored, on the x-axis it is to be mirrored, then you put a negative to that minus the negative sign to the 1 on the first x-axis. If you want it should be mirrored, that means flipped in this angle below, then you put a -1 here, but keep +1 here. Okay, if you put both -1 and -1, can somebody tell me what the answer will be? Try, just say something, it doesn't matter.
It will be in the third quadrant.
Which quadrant?
Third quadrant.
You mean this quadrant, right?
Yeah, that way, yeah.
Yes, exactly. Excellent. So the whole space movement can be handled by matrices. Do you buy it now so far? You can shear it, you can scale it, you can reflect it, you can flip it. In other words, you can move points in the 3-dimensional or n-dimensional. I'm coming to that statement later, okay? In this 2-dimensional, all point movements are easily, beautifully handled by simple and rewriting of these matrices. Everybody buys into it? Say yes, sir, please. No, he's also okay, acceptable. Okay.
Yeah.
Okay, cool. Now, you might be wondering, because you all know determinant, you might be wondering what is determinant, right? Determinant, because I didn't talk about one thing here, right? That is, something is going on here. As all these transformations happen, there's something happening about the volume or the area. Okay, that is given to you by determinant. I'm not going to go into determinant because it's not relevant for us. But you might be wondering, where does the determinant come into play and the A inverse come into play? But A inverse is more important than the determinant. Okay, so I'm going to talk to you more about A inverse, and systems of solutions for systems of equations. In fact, I will never use determinant from now on. Okay, in data science, it's not that useful. Oh my goodness, this guy really gets it to say that, right? Of course. Okay, it's not that useful, but the inverses products matter. Okay, so now given these things on that side, I want to leave that part now. What can we do? I know I went into the area of talking about systems of equations. Why did I do that? Okay, because systems of equations are also called linear systems, right? Are fundamental. Solving for unknowns given various constraints or situations. These are all situations or constraints. Given the constraints or situations, it becomes a constraint when it is a less than or equal to or greater than or equal to. Okay, that's a linear programming. Everybody gets it? Same systems of equations with constraints becomes linear programming. The optimization problem, operations research. Again, I'm not going to go today. I have done that topic in the past. But fundamental is your linear models, which is the foundations for modeling. Linear model. Everybody understand linear regression? Have you heard of it, right?
Yeah.
Okay, excellent. So all of you can say yes also. Some of you are not talking, or you are not able to type today. That's fine. Talk to me, shout. This is a fun place, fun time. Okay. So your linear model or linear regression is again foundations coming from this kind of structure, linear equations. Okay, there your XYZs are really the beta alpha, beta 1, beta 2 like that. Okay, and this is the cross product of what is called the cross product matrix. Okay, x prime x. Okay, x prime x beta here y, and we solve for this is xy actually. On the right side will be xy. No, right side will be xy. This is x prime x. beta, so beta becomes x prime x inverse x prime y. Now, the point I'm trying to say is, no, this is fundamental, and you all need to understand the purpose of A inverse and how do we find that. The common mistake, I'm going to tell you today, the common mistake people do is that, if I ask you to find out A inverse, okay, if you ask you to find out A inverse, how will you find out? Anybody? Just tell me a keyword in terms of the method. What method you'll use? Say something. Anybody? Okay, I'm going to say, you can say yes or no, all right? The common method is use determinant. Is that right?
Yeah.
Okay, one person said yes. Okay, fine. I take that's a commonly used method. You also agree with me, but that is not what you should be using it. You can never solve problems, large big data problems with the determinant. So forget about it. Oh, okay. So what's the method, right? Then that's the next question. We will be using what is called row transformations, reduced form method to solve problem. Does it make sense to you? Did you hear that word? If
I have.
Yeah, I'm pretty sure. If you have done, courses in mathematics and especially, in engineering and this and that, you would have taught. But that's what you have to use. Why is that important? Can somebody say an answer? Can you give me an answer why? Because you would have done it. I'm just asking. I will give you the answer. Can you tell me why you think the row transformation method is the one you are used to solve systems of equations? You want to try? Just say something. It's okay. It's either yes or no, right? I will say for that. Okay, I'll give you an answer. All right. That's the only way you can solve for systems of equations with 1 million variables. Do you buy that? And in huge problems, for example, logistics, UPS, FedEx. I'm in USA. I call about these companies, UPS, FedEx, or I don't know. Oh, it is in there. Maybe you can talk about Flipkart or who is there? Dotmail. Dotmail in your dot delivery. What is that delivery company in India? They all have to use hundreds and hundreds and thousands and perhaps millions of it. I know UPS does solve problem with millions of variables. Okay, you cannot solve the problem any other way. Determinant, forget it. If you have 10 variables, it's a mess. You cannot solve problem with determinant. So you need to use some other method, and the row transformation method is what will help you to find the solutions for large systems of linear equations. Okay, and we are always talking about big data. Okay, so even large linear model, if it is 50 variable, 100 variable, 200 variables, there is no other way. You need to find x prime x inverse x prime y. Okay, we'll talk about x prime. There is an inverse there, right? There's a matrix inverse is there. But the point is that matrix inverse has to be solved using row transformations. So what is it, right? You might be wondering, what is that? This seems to be funny. I have lots of other notes also. For example, here these are all coming from Wikipedia, but I selectively took it for learning from you. For example, I'm kind of a little bit distracting on the graphic side. Again, I'll come back to the linear systems and then PCA, PCA, as well as TensorFlow and all those things later on. Okay, so this is the if you use that, this is called identity matrix. If you use the transformation for identity matrix, nothing happens. But if you want to translate the place, translate means place, move it some other place, then you use this kind of transformation. But you can translate it using this matrix. Use the xy here. If you want to expand scale on the x-axis, w times, y-axis on the h times, that we talked about it, and you can use this matrix as the matrix multiplier. Okay, but it's a three-dimensional point in a two-dimensional world. Remember this, it's a three-dimensional point in a two-dimensional world. That's why the transformation becomes a 3 by 3 matrix. Okay, I showed you earlier only 2 by 2 matrix. So you can shear, using, we talked about the cosine theta, sin theta issues. Here, if you are going to rotate about the origin on the xy plane, you use this matrix. If you're going to shear in x direction, that means this is the x, you're shearing it on the x direction, you use this matrix. These are all mathematically shown, so you don't have to worry about it, you just use them in your graphics programming, okay? And if you want to reflect, we talked about it, reflect, this is the third quadrant, somebody mentioned it. If you want third quadrant, you put negative numbers on this side. If you want on the y-axis, x-axis, then you put the negative on this side. If you want to about y-axis, you put the minus negative here on this side, on this number. So I have other things to talk about. Here is the summarization. It's a quick summary. I want to come to you, come with the conclusion here. If the real world problems are, we always need to deal with a lot of variables. That's what big data analytics is all about. That's what the artificial intelligence analytics is all about. Any variables, which are any number of them, any number of variables can be handled if we know the systematic method of handling matrices or vectors. Vectors, not vectors. There's a typo there. Okay. Why is not? Okay. Why? Okay, here it is. All right. So I want to get to this conclusion, and I want you to get a buy-in from you and ask you and hear out from you whether you buy into this or not. So the columns are variables. In the matrix, the columns are variables, and if you want any number of columns are variables, one variable you want to handle. This is the 1001 column matrix. And let's say you have to handle million observations with 1000 variables, then the individual data points of a multidimensional data is coming on the rows. Individual data points are coming on the rows. The variables are coming on the columns. Think about it very carefully. So if it is 3 rows, 3 observations for 3 variables means this is what it is. And this is the vectors. These are called vector. Okay, vector of data. These are called vector of it refers to the variables, vector variables. But in the rows refers to vector of data points. Rows refers to vector of data points, column refers to the vector variables. And if it is a 1001 variable and million observations, this will be a huge matrix of 1001 columns and million rows, or million rows and 1000 columns, 1001 columns. So far so good, everybody? I quickly moved into big data issues. So are you with me? It's quiet. Are you folks with me? Okay. All right. I take the message you are with me. Because you're not talking, so I have to assume that's not good, but I have to assume. Please interact, that's fun. Now, so the fundamental problem in big data analytics is understanding not only the matrix multiplications, but also matrix inverses. Okay. Not only matrix. If you are not going to interact with in the session, please mute out. If you are only if you want to interact, you do you keep your mic on. Because we are hearing some noise from your home. Okay. All right. So we very quickly went into the idea of the vector representation of matrices and also called mathematical representation of multivariate data. It's all about matrices. Okay. I don't know how many of you are convinced. I am already there right now. Now, the fundamental thing about once the matrices come in, two things are very important: matrix multiplications and the matrix inverse. So, what is it? Okay, and how do we find a matrix inverses in a simple, easier way? Whatever the number of variables you have, 100 variables, fine. 100,000 variables, fine. How do we find it? It is very simple. So I already kind of indicated that. Anybody wants to recall that or say that?
Okay. Why do we need matrix?
Oh, some kid is also attending this session.
algebra.
Please mute out if you are not answering my question.
बल्कि दीदी ने एक बार और बात लिखी, ये लिखा,
Oh
फिर
my
कोई बात नहीं.
All right. Anybody wants to take a shot at the question I raised? Finding matrix inverse is very easy. However many number of dimensions of variables are. What is that method? Anybody wants to say few words? No?
No.
Okay. All right, let's try. So I kind of indicated it's all about row transformation. I'm going to show it to you with a simple two-dimensional data. I talk about it in my class, all these little details, how I got this matrix. Okay, 2, 3, 5, 1, x, y, 9, 16. Okay, that's the matrix I'm going to share with you. Okay, it's really about a fun example of two kids in a family. Mom gives money to buy mango and banana. Okay, and banana, 2 banana, 3 mango. What is that? The story is here. X is the unit of price of mango. Yeah, 2 banana. First day they buy 2 banana and 3 mangoes, and they spend 9 rupees. And then mom gave 10 rupees. So they returned the one rupee, but mom asked, "Where is the receipt?" They said, "Oh my goodness, we lost it." Okay, mom was upset, but she said, "Okay, from now on, you have to give me the receipt so that I can give you exact money next time," right? And then next, after a few days, mom gave some money to buy again mango and banana, and let's assume that the price did not change because otherwise the story doesn't hold good. And then they bought. The mom asked to buy 5 mangoes and 1 banana. And they bought it, and they came back again. On the way, the siblings fought and they lost their receipt. They were fighting about something, right? There is always sibling fighting. They lost their receipt, and they were very afraid to tell the mom, but of course they did. Okay, mom, we lost it. Okay, and they gave 4 rupees back because mom gave 20, and they said we know that it is 16 rupees, and mom doesn't know whether she can believe in that. But anyway. But these 2 kids, smart kids, right? They said, "Don't worry, mom. We know we can find out what the price of mango and banana." Okay? How did they find? That's a question, right? Very simple question. That's what the question we are answering here. So what we are saying is that you can solve this as a system. This is a system of 2 equations, 2 unknowns. You can solve it substitution method. But what if there are 1,000 equations and with 1,000 variables, right? That's a problem.
Yeah.
So how do we solve it? So we can use a matrix method. So write this into a matrix form, and then we can solve it using finding matrix inverse or using the row operations. So what does that mean? Row operations means I'm going to skim all these things right now, and then so basically you put some kind of you are creating a matrix of C1. These are the the inverse matrix values C11, C12, C21, C22. So you write it in such a way that once you multiply this one, because it's the inverse of this matrix, it becomes I identity matrix. That's the property of inverse. Whether you multiply right side or left side, it becomes an identity matrix. That's the property. So on the right side, you are using the same thing, both sides, right? That's whatever that inverse means. You are multiplying here, you should multiply here, then it becomes here. So the inverse. If you can find the C11, C12, C21, C22, you can multiply this thing and solve the problem. That means you are solving for X and you are solving for Y. Now, how do I find that out? Let's go quickly. I don't want to go a lot of details, but you should be able to, appreciate this even if I show you just the this method here. I'm going to show you in a small Excel sheet how you do the row transformations, and then you get the answer. Oh, joy, joy, joy! Something happened. Okay, it should be here. No, it should be here. Oh. 9. Okay, I will go back to okay, here it is. That's fine. So very simple. What we do is, you write your coefficient matrix, that is 2, 3, 5, 1, and then put an identity matrix, and then put the cost here, right? This is, are you with me, everybody? You just do this.
Yeah.
Okay,
Yeah.
excellent. Only two people said yes. Please talk to me. It's fun, believe me, it is fun. Okay, anyway, thank you very much, those who responded. So what we are saying is now somehow make this into a, using row transformations only, make this into an I. That is your job. Your job is use transform. I'm going to tell you what those row transformations are. You make this into I. When you make this into I, whatever happens here is your inverse. Get it? Whatever happens here, you get, that is the inverse of the this matrix. Not only that, this is the price. Whatever here happens, in this row is the price of mango. Whatever happens here is the price of banana. Isn't it cool? Simple setup. Okay.
Yeah.
So what is row transformation? That's all you need to know. If you know it, you have a phenomenal power to solve 100,000 variable, 100,000 equations. It doesn't matter. Okay. I get up. When I saw this and I thought, oh, this is crazy, man. This is so cool. Very simple. Complex problem, very simple solution. Now, so what row transformation means is you can multiply the whole row by a constant. That is one possibility. That constant could be negative, positive, fraction, anything. It doesn't matter. Okay, all real numbers. Or you can multiply one row and add to the other row. You can do. But when I say one row, that means you have to operate on all the elements. Setup is very, very important, and interpretation is very, very important. And then doing row transformation is very, very important. Once you do that, if you implement the row transformation, you know how to solve 100,000 variable to 100,000 equations. Systems of solutions, systems of linear systems. 100,000 variables with 100,000 variables, 100,000 equations. Now, here I wrote this setup, right? I already have it. So I divide this because I want to bring this into an I matrix, right? That was my goal. So ultimately, when I do the row transformation, I have a goal. The goal is make this into an I matrix. So I divide this by 2, and then that becomes 1 and 1.5. It's 0.5, 0 here, and 4.5. Everybody gets it?
Yeah.
Cool. And then I multiply this in the second step. I multiply this by -5. I said you can multiply by a constant. It can be negative, positive. -5, less than 1 or greater than 1, doesn't matter. -5, and then add to this one. So it becomes 0. This becomes -6.5. That's why I put it in a bracket. This becomes -2.5. This becomes 1. This becomes -6.5. Is everybody with me?
Yep.
Yes.
Very fast. You guys are very fast. You all check to the calculator on the right. Okay, cool. Now I got to make this 1, so I divide the second row by -6.5. So this becomes 1. This becomes minus 0.3846 plus this time, and this becomes -1.538. Well, very close, but this is not 0. We want to make this as 0. What do? I multiply this by 1.5 minus 1.5, add it to this row. So nothing happens here, but this becomes 0, and all these things happen here. Whatever it is, that is the A inverse of this. I got A inverse matrix here. Also, very interesting. I already got the price from the cost. I got from the cost I got to price. It's amazing. This is really the linear systems of equation and linear, what is it called? Linear programming also in the operations research. Okay, but I don't want to go there right now. So you got that answer. You got 2 things achieved in this one. One is you know how to calculate matrices, matrix inverses, and also solve systems of equations. Is everybody cool on this so far?
Yeah.
Okay, thank you very much. One person said yes. Okay, now, so I want to stop here, and then I want to just give you some taste of PCA, principal component analysis. The 2 examples today are good enough. Okay, just indications. If I can give that would be cool. That is good enough, I think. So let me go to another presentation I have. Okay, let's quickly show you the setup. Not, I don't want this. I know that's a little bit advanced. I want really the PCA. Okay, let's see. So the thing is that systems of equations are very perfect, perfectly valued expressions. They don't have any errors. What does that mean? What do I mean by that? If it is a statistical data, there are errors in observations. Okay, that's why they are not perfect observation. That's the beauty of statistics versus mathematics. Mathematics is all about perfectly aligned variables. Perfect, there is no error in the setup. But in statistics, everything has an error, right? So if the observations have errors, okay, this is the x-axis, this is the y-axis, but the observations are distributed like this. Can I find out the principal axis? This is a three-dimensional point. Remember that, right? Because there is a z-axis, this y-axis, x-axis. This is into a kind of three-dimensional ellipse kind of thing, right? Three-dimensional ellipse kind of thing. And I don't know whether you can see that. This is a thick red line. There is another thin red line here, dot, dot, dot. And the third one is another thin, light vertical line. Do you see that?
Yeah.
Okay, so that's how it is becoming a three-dimensional point here for you to visualize, right? Maybe it's not very, blatantly hitting on your face, but it is there. This is one of the directions. This is another directions. This is another direction. Okay. Now,
Yes.
what we are saying is PCA is again a matrix method. I am not going to go into the mathematics of it. That is something that we will have to talk another time, or join a data science program. They'll teach you all these things. But what I want to tell you is that the original observation is actually these. These are the variables, and it is centered here. PCA. What PCA does is it translates you to this world, and then it also identifies the axis is the main axis is this axis, neither x nor y nor z, not even z, but it is this axis. Okay. The principal component analysis helps you find this axis, even though there are errors in the observations. Principal component analysis also helps you find this axis, the vertical axis, and this axis. This is another axis. Okay, this is another axis. This is called the main axis because most of the variation is happening here. The next dimension, next axis is this. Not much variation happens. That's why this is thick red color. This is thin red dotted point. There is also a little bit of variation is happening here. So this three-dimensional data with the error is, we locate and identify the major axes and minor axes. That is what PCA is all about. I want to stop here and let you ask me questions for today. That's what I want to bring it up to you to get you excited about the possibilities, the ability to solve complex problems in data science. Any questions that I can answer? It's pretty quiet.
Not really.
Not really. Okay. Here it is quiet. I don't hear. Maybe there is a lot of rain going on there. But I like when students interact with me. There is no other way we can learn from each other, because I learn what your problems are. How you think, why you think in a particular way, and you learn. Oh, I can make you think in a certain angle that helps you solve problems. So go challenge. Go for the challenge and go challenge. And if you don't have any questions, I want to say hello to everybody. Bye for everyone. And maybe we'll be prepared more to talk about hear from you next time. Is that a good call?
Okay. Yeah.
All right. Thank you very much, everyone. I had a fun time. I hope you had a fun time in this fun and power. Can you anyone tell me what is the power you heard from here today? Fun probably you heard already, because it's a graphics application is only matrices you can do. I also said that you can solve systems of equations with matrices. One statement about what is meant by power here, which you cannot any other way solve it, only by matrices and mathematics. What is it? No answer? No answer? Okay, can I say, because you are not giving the answer, can I say the answer?
Yeah, sure.
Okay, no, I'm going to keep it as the search for the answer for you to have that fun. Thank you very much, everybody. Have great evening or great day here in USA. Great evening in India. Most of you, I know most of you coming from India and USA. Thanks a lot. Bye bye.
Bye.
Thank you. Bye bye, everybody.
Bye bye.